not streaming. It says 60 frames a second, 0 drop frames. It's live, it's recording. No echo this time? I'm going to do this again, but really fast. Hopefully this is actually working correct and it's not doing the double audio. The echo, I mean. Wow, that's going to bug me. That was for the painter. I can still see some of the white underneath. Wow, that's going to bug me. That was for the painter. Okay, this is looking much better. If someone can comment in the chat, let me know if there's an echo again. I think I can break this out somehow, or no. Just making sure the stream is going good. All right. Let's minimize this, get this away. Here for a second. Out of this page. Okay, real quick. Where to get my firmwares and everything that I'm running. GeorgeRoblesJr.wordpress.com. There's a link in the description, I believe. The recent post, there's 4. One of them is doubled. I don't know why. And don't want to change it. Don't want to mess with it because for some reason one works better than the other. Go figure. It's in order from newest to oldest. Go to the oldest, scroll down a bit, and you'll get into the different firmwares that basically where I've started off. Arduino 1.0.1 with Sanguine and Lulu options installed, which is essentially you have to add into the library of Arduino um, that microcontroller and the features for it. If you scroll down below, you'll see that I have a version of 1.1 with a U8 glib library installed. For some reason, this link works better for half of the US. The other half of the US can't use this, or can't use the top one. Repetier host for the Geeetech version. These versions of firmware are for the GT2560 legacy board, which means it does not say Rev A on it. However, down here you can see there's also some slicer settings which are useful. There's a few useful things on here, and for the other boards that are still out there, that's why I leave this post. For most other people who have a GT2560 Rev A board, go to my current firmware for GT2560 Rev A. This is a Veroni type skull that printed from Thingiverse. As you can see here, this one's got an open top. It's just different things showing about it. Now this is showing the filament sensor, the casing. You got to paint some of that stuff on the inside. Let's check some. What the heck just happened? There we go. Go figure. Just check something real quick. Okay, still streaming good. Of course, the AC kicks on. Sorry. Okay. If I hit Control 1 to switch to my camera scene, it does something else to get to another web page. My guess is the Control 1, 2, 3 is opening up those 3 web pages at the same time I'm switching scenes. Sorry. Now my AC kicked on, and now the noise cancellation is hopefully cutting out most of it. Lost track of where I was. Here I am. Okay. So the Pro B setup and Pro C setup. The only difference between them is one extruder is disabled. If you want to enable it, that's up to you. Where to get that firmware is going to be right here. Pro B setup, once you click on that link, for example, you will be taken to here. You can extract it right away with zip extractor, or you can download it, which is what I recommend. Download it, keep it on your file. For people who have the x-axis direction reversed or y-axis reversed because of stepper motor position, this is where you can find your firmware's revisions. Here's a link to all 16 different 4 versions, each of the 4 versions with 4 options. These are the 4 options for each of the 4 versions that I did, which is essentially just reversing X, reversing Y, or reversing X and Y. And the 4th one is the original setup. So I provided a link for somebody who wants to get them downloaded all at once. As you see, I have 3 different versions of Arduino. The newest one, 1.04, 1.0.1. This is the one that we're going to run, 1.0.1, but 1.0.4 will work as well. Now, once you have your file extracted into its own folder, you're going to want to open that folder, and there's going to be two INO files, GT2560 and the Marlin. The Marlin's going to be the original setup. GT2560 is going to be the Pro B setup. Now, the Marlin is essentially the standard firmware release that I got offline, or got online. That's the file you want to open. It'll take you to another window. You can close your previous window, maximize this window. Configuration.h is going to be the file where you make all the changes. Running through this, it's pretty much self-explanatory as you read it. This is the string version that I'm currently running, 1.0.2. I don't know what string it is. When I modified it, there's dates that I've modified it somewhere. Maybe not on this one, on a different file I did. I just put down Geeetech Prusa config georges3dprinters.com. So basically, who did it? If you change it, author it. Put it somewhere on the GitHub. I don't do that. Other people do that. If you like it, share it. Otherwise, it's like I put the stuff here for anybody to view. The baud rate, 250,000 kilobit per second is what it's pre-set up. You can set it to whatever you want. If you want it so like only you can access your printer, you can set in a funky baud rate and then set that same funky baud rate in Repetier host, for example. Just don't get too crazy with it. If you wanted to enable Bluetooth on this printer, and you didn't want to use, say, a second extruder because you're running a Rev A. In my case, I'm running a Filament Sensor, but instead of the second extruder. So instead of doing that, you could run, like, say, a Bluetooth chip for communications. Now you got to get into the TX and RX of it, but you can change it, the pins inside firmware. Best way to get to that is get into File Explorer using Notepad++. Look for the pins.h file. Oops, skipped it. Open with Notepad++. It'll bring you into a folder that looks like so. And it's actually arranged correctly. If you open it with just Notepad, there's not going to be any spaces. This file is huge. Like, how many thousands of lines? Let's see, 3,090 lines in this. The reason why it's so long on this specific tab is this is a list of all the boards that are handled by this firmware, and the pin layout for each of the boards is different. So if we just hit Control F and we want to look for GT2560, now we can close the search. Control F is just you're bringing up a search engine. As you see, I've added this GT2560 to the firmware setup, so it doesn't say Ultimaker board. And these are all the pins that have been assigned to it. So if you were to look at the pin layout for an Atmel 2560 microcontroller chip, these are the pins that will be, they will show you the pin locations on the diagram. That's how I found out where to put my filament sensor wire for the analog input that I needed. If you see a -1, it's a pin that's disabled. So for example, heater pin 2. So extruder 2 has been disabled. What else is important for this file? if your controller knob, if your LCD knob is rotating in the direction that you don't want it to, so if you want it to go clockwise instead of counterclockwise, then you can change these two numbers right here, BTNEM1 and BTNEN2. So pin 42 and pin 40, flip them. So 42 will be where 40 is and 40 will be where 42 is. Then your direction of your scrolling on your knob for your LCD will be reversed. In my case of my firmware, I've already set it up so it turns clockwise. If you make any changes to a file, you can save it and it'll get saved to that file. However, don't do it unless you got a backup copy, willing to take the risk. And speaking of risk, don't blame me. This is all at your own risk. I'm just teaching you. Take it for what it is. Knowledge and learn it. Now Bluetooth I don't have enabled because I'm running the filament sensor. The more you add to that 5-volt rail, the more strain you put on it, so don't put too much. Okay, define motherboard. I've added GT2560 to this, which is why it says that, not Ultimaker board. If you wanted to have your own machine UUID, you can go to this website, thegenerator.net version 4, and get essentially a serial number for your 3D printer. Extruders. So right now I have it as 1. For Pro C, you would change that number to 2, along with other numbers. Power supply. The ATX basically means it's a standard computer style power supply. It's a regulated power supply, and it's a certain set of parameters it has to reach. The Xbox is kind of a weaker one, don't use it. The heat bed alone can pull up to 300 watts sometimes. Thermal settings. Ah, damn it. Okay. Let me, let's just look. So thermal settings. This is a list of the different thermocouples or thermistors or thermal resistors that you can use on this printer. Here are the specifications. The numbers that you see to the left are the numbers that you want to use. If it's 0, it means it's disabled and not used. In this code, extruder 1 is extruder 0, extruder 2 is extruder 1, extruder 3 is extruder 2. And that's when it comes to like here, this temp sensor. Code starts off with 0, and that's the first digit. So extruder 1 is 0, and that's why it works that way. So each extruder is labeled down this column right here. The column on the right is the reference to this number. So your thermocouple that you're using is going to be plugged in here. If you have a second extruder, plug that in. Third extruder, etc. Now the heat bed, again, has, in this case of the Geeetech, the heat bed and the hot end are both the same thermocouple. Well, I don't know now, but it used to be. Let's see, where am I at? Max temperature sensor, one redundant sensor. It's just redundancies, stuff like that. Let's get into where it's important. Minimum temperature. The reason why I have -5 degrees is because I live in the high desert, which means I'm up in the mountains, behind the mountains in a desert, 6,000 feet above sea level, something like that, and it gets cold. Where I keep my printer in the garage, it can get below 0 degrees centigrade, which is freezing. Water freezes at 0 degrees centigrade, or 32 degrees Fahrenheit. Everything on this printer is in Celsius. So -5 degrees Celsius is below zero, below freezing, but not necessarily below zero for the Fahrenheit scale. So whatever. Basically what this does is if it's below the minimum temperature, your printer will say there's a minimum temp error, I'm not going to print. The way I used to get my printer to print before I switched it to -5, because it was set to 5 degrees before, I would put my hand on the heat bed, wait for it to come up to above the 5 degrees centigrade, and then on the hot end I would also hold it and wait for that to come up above 5 degrees centigrade. So in order to avoid all that, and then the speed of having to turn on your printer, turn the knob, kick on both heaters just in time before it cools back off because everything else is still freezing. Yeah, it's amazing what the human does when they're lazy. So I was lazy to change the firmware, even though it takes like seconds and half a minute to upload. All I had to do was change that. But I never did for like a year and a half. Max temperature. For this setup, this MK8 layout, it's got a PTFE liner, which is a Teflon tube, 2 millimeters inside diameter, 4 millimeters outside diameter. So if you need to order more, that's the sizes. The max temperature of this is pretty much 500 degrees centigrade. It's a little bit above that, but pretty much 250 degrees Celsius, you're going to be burning your PTFE liner. Very slowly, but not too slowly. But you're going to be burning it slowly, let's say. And if you're going to be printing at high temperatures, such as for like polycarbonates or polyethylene PETG, things like that, higher temperatures, you might want to switch out your barrel with an all metal barrel versus the PTFE liner barrel. PTFE liner provides a heat break, essentially insulating heat from creeping up to your barrel into the extruder gears and then melting the filament instead of moving the filament. Max temp for the bed, I wouldn't go above 110 for this kind of setup, and that's even pushing it. That's like the max. When I print, it's 90 or 100 degrees Celsius. That's ABS, and I usually put like a box around it. I've already done this once, and there was an echo. Thank you 3D Printing for catching that. So I'm doing this again, and I'm trying to run through this fast. Before it was more shooting the breeze. PID loops, this is what I'm getting into now for the hot end. I've set up numbers and attached what I got for my setup. This gets into the bed. This also gets into parts like where people want to go extreme and use a silicone heater, 1000 watt heater plugged into the wall, being controlled via a solid state relay via your Arduino or Arduino Mega and RAMS 1.4 or GT2560 or Ultimaker board, etc., etc., etc. PID loops that I've set up, as you can see, are what worked with for my setup. Tune it for your own. That code is right here. N303, and getting into G code. Marlin main. We'll open up this tab, scroll down a little bit. Here's a list of all the G code that is implemented in with this printer. So if you want to know what the G code is, here it is. G1 is going to be the one that's going to be used the most. G28 for homing, home all access. G29 is if you're going to be homing with the Z probe, so auto leveling. Now, G28 will home all the accesses to 0. G29 will home out X and Y, and then move to the center and then home out Z, and then touch off on the 9 points for my setup. Some people use a 3-point setup, or a 3-point grid versus a 9-point grid. So, one thing about 3D printers that they don't use is clockwise and counterclockwise arcs. This is a specific movement that's programmed into G-code for CNCs that run G-code. So that's my experience, is running a Como VR512 CNC router. It's a 5-foot by 12-foot CNC router table, wood router table. It had an automatic tool changer on it. And now my dad's company, he sold that one, now he's got another one. He's running a SCM group, made it in Italy. SCM group CNC. This one's got a mobile gantry, stationary table. The Como had a table that moved back and forth, just like this. A stationary gantry, which is the x-axis that moved back and forth, and then your z-axis moved up and down. Same thing on the CNC router I ran. And back to my point, CNC routers, they G-code, those CNC machines, they utilize the counterclockwise and clockwise arcs. It's actually really good for circles and things like that. However, in 3D printing and the way slicing works and extruding works, they don't do that here. They don't utilize that feature. It's a series of bunch of straight lines with a certain amount of extruded material to be extruded during that movement. So that's G-code in a nutshell. Now back to this. M303 is the G-code that it's going to be calling up, which is essentially running a PID loop tune. E1 is going to be the loop that you're going to tune. So in this case, E1 is the heat bed. E0 is extruder 1. E2 is extruder 2. Why they did that in that order, I don't know. It just is, that's the way it is. C10. Now, most people have this as C8. 8 cycles is what it stands for. So C stands for cycles. The number after it is the amount of cycles you're going to run. If you run 10, it's better for your math and a better average overall for your PID loop tuning. S is going to be the temperature that's going to be set. So in the case of the heat bed, I went for a target temperature of 90 degrees Celsius, which was my low heat bed temperature for ABS. The high temperature for ABS that I run is 100 degrees Celsius, but 90 is close enough. And this will run for 10 cycles, not 8 cycles. So now this description is correct. M303 E1 C10 S90. This will run 10 cycles of the heat bed at 90 degrees centigrade, and then afterwards it's going to spit out a few numbers of KP, KI, and KD numbers. When you get those numbers, you're going to plug them in right here for the heat bed and right here for the hot end. Each one is labeled, so extruder, look for that, then plug it in for that. Heat bed, plug it in for that. And you'll see it says default bed KP, and then a huge number versus like the hot end. And basically what the PID loops is tuning, essentially. What it's doing is it's averaging how fast it gets to temperature with how much power. If you're running a PID loop, it's much smoother in how your printer achieves a temperature. Otherwise, it's the bang bang setup, which is full power on, full power off. That's what they mean by the bang and the bang, because they're signifying like the, your full throttle to the metal, Bang bang, the way it works is full power. When your temperatures hit, it shuts off the power, but your temperature is going to exceed that point because more power is fed to it than needed. And as that power draws back down, it'll pass your target temperature, and then when it gets to a few degrees below, then your heater will kick back on full power, and then to your temperature is then exceeded, and then shuts back off, and it keeps doing this and keeps it within a certain range of temperature. If you tune your PID loops, you're not doing the bang bang no more, but rather you're ramping up to your temperature, and then you're stabilizing, and you're staying there. If you want to try to apply it to a graph, it would be a gradual ramp and then a shelf, and very little variances. And that's ideal, and that's what you're going to want to do. Your hot end. Prevent dangerous extrudes. So basically, if the temperature is too low, you're going to set a minimum extrude temperature of 170, and you cannot extrude below that. One customer that I had for tech support, they had to extrude at 100 degrees Celsius for a flexible filament they had that they were trying out. So they had to change this number. They called me up and tried to figure out how they could achieve that lower temperature. However, if you try to do that with other filaments, you're risking messing up your nozzle if your temperature is not at the right temperatures. The minimum temp, the reason why it's set in firmware is so that it's kind of like a hard, it's like a second backup to say stop for the printer and stop printing because you're not printing correctly. Prevent lengthy extrude. I'm gonna go back up a little bit. So prevent dangerous extrude. Pretty much it's like saying don't extrude unless it's safe. Prevent lengthy extrude. Your heat block can only retain so much heat energy, and the filament that's fed into it that at room temperature is going to be taking that heat away in order, it has to absorb that heat energy in order to melt and then be extruded through that nozzle 1/20th the size of its diameter. So you cannot feed too much filament into a heat block that only has so much heat in it. If you look at the Task 6, the Morse extruder, they have a huge heat block now, and that's that residual heat that they need to feed a 1 millimeter nozzle or 1.2 millimeter nozzle. You can do it with 2 millimeter filament pretty much, or 1.75 millimeter filament. And it would probably extrude very fast, let's say, because the Task 6 heater is huge. Now they're running a Wade's extruder, so that stepper motor is like flying. So back into the minimum temperature. When you're extruding, and say you're doing a rapid movement, or you have a nozzle that's using a lot of material, in order to prevent the dangerous extrude, it will calculate the BTU thermal energy contained within your hot end plus the energy that it's feeding into it via the heater, and then try to figure out via math and an algorithm and whatnot to how much filament that's going to be fed in. So if it knows it's got 100 millimeters of filament coming, it knows not to use it all. And if it comes in all at once, then the secondary redundancy that it has to stop is that when the temperature hits 170, then it's like a hard stop, like saying, okay, that's it, I'm cutting the printer. Thermal runaway protection. This is actually very important for people that keep saying that the printers are burning up. If a wire breaks on your thermocouple that goes to your heat bed or to your hot end, it's going to read basically 0 degrees Celsius, and then your printer is going to be like, whoa, the temperature just dropped down really fast. Let me give you full power and try to bring it back up. Thermal runaway protection looks at how long it took for the temperature to change. If it says raise the temperature 5 degrees and in 40 seconds it doesn't reach 5 degrees, it's going to stop the print and say there's a thermal runaway error. You can adjust this number depending on your setup to fine-tune things. Some people have a really thick heat bed, and then by the time the sensor heats up versus the bed around it, it can take, like, say, a minute and a half versus 20 seconds or 40 seconds. So the bed, I believe, is parameters for all extruder heaters, 40 seconds and 4 degrees and change. Now you can change the degrees and change to a smaller number, but that's up to you and your own risk. It's a good thing to implement and a good safety feature to have, because say if one wire breaks from the constant movement back and forth of your hot end or your heat bed moving back and forth, that wire can become fatigued and break. When that happens, it's better for your printer to just stop, lose the print, and I'll show you how to save that later. It's better to stop and lose the print than to let your printer burn up and then not be able to print at all. It's common sense kind of a logic for that setup. Mechanical settings. This gets into the end stops, pull-up resistors, which is not too important for people that are not building the circuit. It's essentially just a resistance between your power rail and your ground and your signal. Or excuse me, signal and ground. For auto level, you'll see this logic right here invert from false to true, because in the case of my auto level setup using a tactile switch, it's a normally open switch. When it's actuated, it's closed. The way Geeetech has their printer set up right now, it's normally normally closed until the printer's in the home position, then that switch is opened. If you're using the two outside wires of that 3 terminal switch, and you'll see on that switch NC, NO, and common. Excuse me 1 second. Thought I heard the door for a second. It is 9:40. Okay, wow, it's way late. I owe my fiance an apology. Okay. Mechanical settings. So that was for the end stops. We're going to go below this, and pretty much disabling an inactive extruder is the only thing that you're going to be wanting to, the only extruder motor that you want to be disabling. Invert XDIR, which this signifies the stepper motor direction, and this is labeling what axis the direction, what axis you're going to be inverting the direction. For people with printed parts, the stepper motor is on the back for x-axis. For people like with the Pro X or metal brackets, the stepper motor is on the front. So your x-axis would be running opposite to mine. So instead of having this true, you would change this logic to false. And then that would invert the direction of the stepper motor, or not invert the direction of the motor, stepper motor. For people with the wide bed that work better with the motor on the right instead of the left, of course, inverse this logic. Z, unless you got reverse threads, this is pretty much, you're not going to change this direction. Extruder 1, extruder 2, which is what I want to touch on for people with running a Pro C. Extruder 1 will rotate this way, and extruder 2 rotates this way. Obviously, one is counterclockwise, one is clockwise. And depending which way that's set up, depending which orientation your stepper motors are set up, you're going to want to change this from true to false or false to true. So you'll change that logic in these two spaces, this space here and this space here. End stop settings. So Geeetechs are pretty much, and most other 3D printers have minimum home end stops and not minimum and max. Some printers have both, some printers have only the max. For example, Delta, they have the end stops on the home in the max position. So they would home to the 1 position, not the -1. In our case, -1 is bringing all the printer axes to 0 in the minimum position. So Z0, X0, Y0. And that means your printer nozzle is going to be parked on the closest towards you to the left, and that Z nozzle is going to be on that bed corner. Software end stops. Basically, this is implemented because your printer will never go max out past to the point. Once you home your printer and the max position, the max travel limits that you have set up below here, when it homes, you can only move 206 millimeters. Unless you skip a step, that's what it's going to do every single time. So move back and forth 206 millimeters. And that's what's going to be set in the firmware, software, so to speak. Now the X position, minimum 0. You don't want to go below 0. In the cases of auto level, a few things are different, but we're not going to touch on that today. Max position for the Z is 180 for me, sometimes 190 depending on the print. And the reason why it depends on the print, bring over this Pro X for an example. Now you can see if this cable runs into this LCD knob, you have a problem. Same thing with your filament, anything that runs into this, that's going to cause a skip step. Is basically a physical interference is going to be a physical interference and cause a problem. Bed leveling, auto leveling. I'm not going to touch too much on this except for the grid and the 3-point. That speaks to the accuracy and how much strain you're going to put on the microcontroller unit. 3-point grid, which, 3-point versus grid. Grid, you put in how many points you want to touch, they get multiplied by 3. So if you hit 3, you're actually touch off on 9 points because it makes 3 triangles, and each of the 3 triangles add up to 9 points. 3-point mode is essentially finding the level of one triangle. So 1, 2, 3, and then it can tell where that triangle is in the plane of the XYZ world that it's programmed into. It gets complicated as far as algorithms, mathematics, so we're not going to touch off into it too much. Other than that, the 3-point is less accurate. The grid mode is more accurate, but more strenuous on mathematics, more on your microcontroller unit. There's more features about offsets of the probe, things of that nature. Manual homing switch locations. We have it at 0, 0, 0, which basically means it's going to move to the minimum points, and that's where it's going to be home for me. If you were to set them to a different position, like when you manually home your machine, it's I'm not going to get too much into that. If you're a CNC machine operator, you'll understand why you have those, and I'm not going to touch off into it for beginners too much. Movement settings. Define the number of axes for X, Y, Z, and E. I don't remember if you have to change this number if you have a second extruder to 5. I'll have to touch on that later. I'm going to be doing dual extruder setup. I have a TiVo Tarantula that was sent to me that I've started production and ended a few times. And I'm trying to stay committed to my commitment and complete that. Movement settings below that, so when it says define homing feed rate, this is just the feed rate for the homing. It's multiplied, so the order of the numbers is X, Y, Z, E. And as the common space that, and that's going to apply to the steps per unit, the feed rate, acceleration, etc. The homing speeds right here, as you can see, it's self-explanatory. It's millimeters times a minute, and that's going to be the feed rate. Defining the steps per unit. Now, if you use a Prusa calculator and punch in all your information, you're going to come up with 80, 80, 2560 for the Z-axis M8 threaded rod, and 95 for the direct drive extruder. The reason why I run 78.74, for some reason the Geeetech stepper motors, they're the ones that I was running anyways, they run much smoother at 78.74 than the numbers that were given to me by the Prusa calculator of 80.0. Now the accuracy is still there, and you can change your compensations via slicer, increase a part, or shrink a part by percentage. However, I'm going to just recommend that you try this on both ways. Home your machine with the other one enabled, so we'll disable that by adding the 2 slashes, going up above and deleting the other 2 slashes, and then like verify it, upload it, try that, listen to the sound that your printer makes, and then come back here, add the 2 slashes, go back down and enable the 78.74 version, and you will see that that one is going to be much smoother and quieter for your 3D printer. It's the best way to explain that. Just try it for yourself and see. I forget how I came up with those numbers. There was a lot of trial and error in the beginning. The first 2 numbers refer to X and Y. The third number refers to the Z-axis, which is the rotation of a threaded rod and the travel that you will have rotating that threaded rod to achieve 1 millimeter in travel in the Z-axis. So if you rotate this 2,560 microsteps, it will move 1 millimeter in distance upward, or a positive from 0. 95, the fourth number, it means 95 steps per millimeter of filament that's fed into your hot end. Mine's is a direct drive. For people running like a Wade's extruder or a geared extruder of some sort, then they're going to have like a number like in the 400s, 800s, or whatever it is that they have for their geared down setup. A quick note on stepper motors. A circle, 360 degrees, right? A stepper motor that steps 1.8 degrees means there's 200 steps for one full rotation. A better stepper motor is a 0.9 degree step. So it steps 0.9 degrees for every step. And it will have 400 steps per revolution. What micro-stepping does with the stepper drivers that we have is it takes each one of these 200 steps and cuts up each step 16 more times. So you end up with 3,200 steps per one revolution. Just a quick rundown on the stepper motors. If you use the 1/32 microstepping, then your resolution for one rotation of the stepper motor goes from 3,200 steps to 6,400 steps. However, trying to do math when you're involving the numbers 1/32 to 1/16, the amount of digits that are increased to handle that amount of math is more strenuous on your microcontroller unit and will slow things down. If we're going to use the purple or blue stepper drivers, blue if they're open source, RepRap, purple if they're Geeetech. Or if you want to know them by numbers, they're DVR8825s. They run 2 amps, 2 to 4 amps that they can run for every stepper motor. Now, the DVR8825s can microstep 1/16. If you're in a pinch and you don't have any of them around, you need to step 1/16. But the max that they can step is 1/32. When they do the max step of 1/32, it's just more strain on your printer, and you don't want to do it. If you're trying to increase resolution, you'd have better luck changing your stepper motors from the 1.8 degree steps to 0.9 degree step. It's just much better that way, and better on the MCU, speed of things. Default, okay, back into this. Default max feed rate, acceleration, default acceleration, retract acceleration. Default acceleration for printing, your slicer is really going to be the thing that determines that. For homing, for other mechanical features, your basic settings that you're programming into the printer, what we're punching in is essentially the limits of what your printer can achieve. But because of the limitations of your extruder and how fast you can melt the plastic and shove it out through a hole that's 1/20th the size of your diameter of your filament in a precise manner, the speed is not there necessarily. So you never essentially reach these maximum default max acceleration speeds. However, when I worked for Paramount Pictures, and that's all I can say due to the NDA, well, I'm going to say a few more things that should be allowed. I was looking for faster speeds in my printer. And in order to achieve faster speeds, one can increase the current going to the stepper motor, which increases the noise level as well as the temperature that everything operates at and the power consumption that's required. I have the current turned up so much that I can hold the extruder and my printer will slide side to side for the X movement. If I were to hold the bed, the printer then moves back and forth when I'm holding the bed. That's how strong the current is, and it does not skip a step. If you want to try to find a physical way to try to achieve that current versus using a multimeter and a screwdriver set to 2 volts, trying to adjust it that way. The accelerations of feed rate is actually more significant. My brain's fried. Sorry. I'm going to try to zip through the rest of this because we're just about done. Define X, Y jerk. So when your printer reaches a resonance, when you're printing like a step step formation, you'll get like a machine gun sound. And sometimes people don't like that sound, so you can adjust this sound to essentially slow down the movements for those kind of resonance that you hit printing. Additional features: EEPROM chit chat and EEPROM settings I've enabled for my firmware so that you can make more adjustments to your printer via Repetier host or Octoprint or Simplified 3D, whatever you want to use. But by setting this up and implementing it, you're able to make changes. Now this does add some to the firmware, some density, essentially. The more options you enable, the bigger the firmware becomes. The bigger the firmware becomes, the slower things happen, because it has to run through this whole file and execute every equation as it's going through all these tabs that you see up here. One microcontroller unit's doing this all via math, you know, and this little chip has got to handle all this math. The more math you give it, the longer it takes to complete the math. So you try to limit how much math you want it to do. So, you know, like you don't give a kid 6 hours of math homework, you give them 30 minutes or an hour, because he needs more time to do other stuff. So in the case of like controlling the heater, the LCD, the microcontroller unit is reading off an SD card. Now taking this instruction from SD card and then saying, okay, these are the instructions. What do these instructions mean? This is what this digit means. This is what this digit means, so on and so forth. And then it figures, okay, this is what this all means. Now I got to do something with these digits. I move this to this file and plug these digits into this equation for this to happen. Now, this is essentially what your microcontroller is doing, except at lightning speed. And sometimes you want to change these features via EEPROM chit-chat. So like things like the feed rate, the steps per revolution, things like that, that's what you want to be able to adjust in EEPROM. And EEPROM has also got a benefit of, in your firmware you have one set of settings. In your EEPROM you can put in another set of settings, and this is saved in a part of the memory that's saved as kind of like flash memory. So you're using part of the memory to store settings and keep the settings there. And every time you turn on your printer, it reads what it has for standards, then it says, okay, is there any other preset settings that are different? It'll get it from the memory, punch those in, and then continue starting up. So EEPROM chit-chat is actually beneficial, but if you need to minimize your program for, say, running a full graphics LCD on Sanguina Lulu, then you wouldn't enable EEPROM chit-chat. You would actually disable it, because you're trying to, you want your code to lose weight, so to speak. You need it thinner, smaller. Preset temperature settings, you can adjust what you want, put in what you want here. The 255 for the fan is just the max setting for that fan. Define LCD to support. Now this has got a bunch of stuff that you can enable by just deleting the 2 slashes in front, if you know what you're doing. If you see here, I have added a line where it says encoders, what is it? Define encoder steps per menu item. And then you have the pulses per step. So basically, think of it like this. Every encoder, whoever makes it, they can be a little finicky. It could have 6 points of contact, it could have 5, it could have 4, whatever the case may be. The point is, you need to fine-tune this for your encoder. So the first item underneath the RipRap Smart Controller, where it says pulses per step, this I added in so that, like, if you want 2 clicks that you physically fill, we'll do 1 movement on your LCD. I tried that out. There was a pain in the butt. I didn't like it. So I switched that back to 1. Every click, 1 movement on my LCD. Encoder steps per menu. Now the 5 I've punched in because it works better for some reason than 6 or 4. Logically, they're usually in pairs for the rotary encoders. As far as the pins go, it's 2, 4, 6, 8, so on and so forth, whatever. The point is, it's usually an even number. But for some reason, 5 works great on my LCD encoder for my Pro V, so that's where I leave it. It's kind of like a trial and error deal for anybody else out there. If you didn't want to use the RipRap Smart controller, then you would add the 2 slashes in front here. Now these steps right here I've added, but it's actually up here already. So like this step right here is a copy, and I've just moved it down here so it's easier to point out for other people. That's the only reason why I did that. It's just I copied it and moved it down. It's just redundant. So right here, by adding those two gray lines, I've disabled that. I'm going to re-enable it, right? If you wanted the full graphics LCD, then you would go to where it says the define wrap discount full graphics smart controller. And you delete the 2 slashes in front of that, and that's the one you'll be running. Make sure you only have 1 enabled, don't have 2 enabled, it'll give you problems. Below this gets into different settings for the LCD. So you can make your own custom LCD. Not all LCDs have an encoder. Some have 5 buttons. Some have 1 button. Some don't have any buttons. If you just want an LCD, you can display the LCD. If you just want an SD card, you can buy the attachment for just an SD card and then only run an SD card in the firmware. But however, you can fine-tune your LCD if you want to try a different LCD. Now, the 2004 LCD is essentially 4 pixel by 20 pixel digits of LCD, and there's so many of those digits on that display. Now, the full graphics is I think 64 pixels by 84. I forget how many it is. But that's what it stands for, the pixels amount, and that's the one, that's the essentially the pixel screen that you have to work with to make graphics, or a digit, or something like that. Come on, voice, come on, start. There it goes. Okay, nice cancellation, love it. My microphone keeps timing out after 10 minutes, so it's 10:04. I was supposed to be home like at 8:30. Jeez. Okay. So encoder steps, LCDs, making your own custom LCD. This is where you want to get into these features. Gets into stuff with like shift registers, and if you don't have enough pins, you use a shift register so you can add more pins to your setup. We're not going to get into that. Get into an Arduino training class for that. I'm assuming you have basic Arduino skills. If not, this is pretty much like I'm walking you through some of the things just to get by. Get back and check some real quick. LCD. LCD. There's some stuff about fan, Pwm speeds, self-explanatory. It's explained in there. A few couple defines for different features. If you have a Canon RC1 remote, you can hook it up, reassign the photograph pin, and then enable it in your your slicer scripts to take a picture at the end of a layer or something. In my case, I just use Octoprint to make my time lapse. It's much easier to use a Logitech camera so I can watch my print via web page, any device, or I can also make a time lapse with that same camera. RC servo support. So basically, this section just gets into the fact, like a ramps board already has breakouts for the servos. Now there's boards that you can plug into those 4 servo outputs and hook up like 2 fans for PWM, but it covers up the other 2 pins. But if you solder onto those 2 other sets of pins, you can still run 2 other servos. It gets complicated. On ramps 1.4, you're still going to need to double up your 3.3 volt and 5 volt regulator, which is one little black chip right by the power input. I take a second one, stack it on top, bend the tabs so it touches it, solder that to the one already on the board so that I can essentially parallel that power supply that's on that chip. So it's bringing in the 12 volts and regulating that down to 5 volts and 3.3 volts for other functions on the board. By adding a second chip, you're essentially having two power supplies running in parallel, removing some of the strain. So in my Ramps 1.4 board that I'm currently making and testing, I have the Bluetooth, I think the 132nd DVR AA25 stepper drivers, and PWM fan control. I'm not sure if I'm still going to do a servo control, but I'd be able to run all that even with the full graphics LCD and still power it all and not burn it off because I've stacked a second voltage regulator to it. Sometimes stacking 3 may be a necessity. It depends how overkill you want to go. Other people just remove it, like RWG Research on YouTube. He blew the chip out, didn't have another one handy, so he, I think he had a 3.3 volt regulator, and then he added in a 5 volt power supply to feed the 5 volt. Just remember, all your grounds have to be tied for logic communication purposes. So servo support, the most common thing used for servos on 3D printers is deploying a Z probe, and the other thing is like cutting a piece of carbon fiber filament that's being laid onto a part. You need to enable the defines like so. Just delete those slash marks, enable which one's active or inactive, and then you got to set your positions, your extend and retract angles. Other people cover that great. I don't like using a servo because that adds more to the firmware, and I didn't have a pin to break out for a servo at the time. So I set up my Z probe as a magnetically latching probe that could be retracted via G code, but has to be manually deployed. Filament sensor, self-explanatory, sort of. This filament sensor just doesn't detect that filament is present. What this does is using a sensor that someone created that someone sells for $60 on Etsy or something like that. It has a smaller microcontroller board that essentially has a scanner, and it controls a LED. It casts a shadow onto the scanner bar. It counts the pixels that are dark versus the pixels that are light. The person who created this board, the filament sensor, you get the board and you gotta hook it up to your analog input, 5 volt and ground. Then on this board it has screw terminals to hook up the 3 wires and also hook up 2 wires to LED. He'll give you the LED, the board, and the pin to calibrate the board. On my 4th blog post you'll see it. The bracket that I had to print out, the links, everything. The guy gives you everything that you need to even make your own board and program it and everything if you can figure that out. Once you have that set up, what this essentially does is if you're using it standalone with the multimeter and you push the button where there's a flashing LED on the board. If it's flashing, it's for measurement via voltage. So voltage is a direct representation of the millimeters that it's measuring. So, and it's measuring in hundredths of a millimeter. It's accurate to within 500ths of a millimeter, which is pretty good, darn good, considering that you're measuring via light and a shadow. And the firmware is also set up here that it takes the measurement, plugs it into some math, and figures out that it either needs to increase your flow rate or decrease your flow rate. So instead of just saying like there's no filament there, this is saying your filament is getting skinnier. I need to increase the flow rate so that it prints exactly the same. This filament is too thick. I need to reduce the film, the extrusion long day. So you get what I'm trying to say. I'm so burnt out, so tired. It's like the third time I'm trying to do this stream. I'm streaming from a hotspot that I ended up going through USB because I had to charge a phone as well. Yeah, I was supposed to be out of here like 2 hours ago. Anyways, so back to this. So the filament sensor. This just does more than just detect it. This part of the firmware detects the filament, stores up to however many centimeters that you plug in into a buffer, and then uses that buffer as the printer is printing. So the reason why you need the buffer is because the filament sensor sits on top, and it's so many millimeters away from the nozzle, the hot end. And the way the math is figured is from where it exits the sensor case, that to the nozzle. So you just kind of take like a guesstimate measurement and punch in a number that's close enough. So if it's less than 10 centimeters away, you punch in like 10, 15, 15, so on and so forth. That's if you have it enabled and are able to solder a wire to the analog pins 4 or 5, which I have set it for. I have it set up for 4. So that's my firmware that I'm running Essential Rundown. Now, once you have everything set up, like say you plugged in all the numbers, you want to figure out what's going on. You're going to verify the sketch. This check mark verifies, this arrow will verify, then upload a sketch to a board. This will open up a new window, so don't ever touch that. This basically opens the next one, next, I want to say file. My brain's fried right now, I can barely function. Next button is save. I don't like using this button, mainly because if you just click save, you'll overwrite that code. Now, you saw when I was accessing my folder, I have multiple firmware layouts. So I always like to click save as, and then label that one accordingly. Once you have it saved, verified, if this is compiling the sketch down here, that's good. I'm going to click to tools. Now, depending on the board that you're running, and in my case, I'm running a GT2560, which is a Atmel 2560 Mega chip. So the Arduino Mega or 2560, the Mega 80K, that's the board I'll be running. The serial port is whatever serial port shows up when you plug in your USB. Programmer, I run Arduino's ISP, and that's pretty much it that you'll have to set up there. Once it's done compiling, go ahead and then compile and upload. Make sure everything's uploaded correctly. It'll say done uploading down here below. So as you can see here, the reason why I compiled this is I wanted to show you the number. The memory I have available is 258,048 bytes. Currently, my firmware sits at 117,532 bytes. So my firmware is currently using half of the memory available. It's way too big for like a Sanguino Lulu. You would not be able to run it. It's too much, too big of a firmware. Each board has so much memory allotted to it. So
I love a Sanguino Lulu because you can swap out the chip, you can swap out it's easier to change the MOSFET, it's easier to repair that board. But it's limited in cases of how many pins I can hook up to it without using a shift register, the speed that it operates at, and how big the memory is. So that's why I went to the GT2560 myself personally. Y'all have a good night. I'm pretty much done with this. I'm going to see what's going on YouTube. Let me first switch this back over to just and see if there's any comments. I don't see any comments. Don't see any complaints. Peace out. Have a good night. If I could end the damn stream, where the freak it go?